Hey everybody, this is Chapter 5, Part 3. We're going to take a look at thermal properties of materials and where and how much to insulate. If we take a look at where where energy is used in the United States, if you want to break it down into sectors, industrial is 33%, transportation is 28%, and buildings are actually 39%. So this is a pretty important topic in terms of how much and where and how we go about doing things when it comes to insulation. So if you put things into perspective, most of the energy used in the United States is related to the topic that we're discussing today. The discussion of thermal properties presented so far leads to two questions. Which parts of the building should be insulated, and how much insulation should we use in each of them? To answer question one, where to insulate, it's fairly obvious. It's the building envelope. The building envelope is what separates conditioned spaces from the outdoors. And how much insulation do we have to use? It depends. It just varies depending upon climate, economics, and the energy code. Related to where we should insulate, the building envelope. The building envelope is basically located, this red line here. It's the part of the building or the structure that separates unconditioned space from conditioned space. So you can see we've got a 3-story building here. We've got a basement, first floor, second floor. There are attic spaces and there are basement spaces which are not insulated. So insulation is what's going to separate us from, the outside or any space that's inside that's unconditioned. In terms of the climate, we're looking at a map with 7 different climate zones in the U.S. And these zones are basically set up dependent upon how many heating degree days and how many cooling degree days that we have. And right here in the Midwest, we are near St. Louis, Missouri, and we would be in Zone 4. So we're going to be in Zone 4. We'll keep that in mind. And Zone 4, if you look at this, it continues from the East Coast all the way through the Southwest, and then it pieces up to the Seattle area. And actually, this part of Zone 4 is a marine Zone 4, which is a little bit different. So we'll take a look at that in a few minutes. So back to Zone 4, it looks like there are 3 different areas of Zone 4. I've got a 4A, which is mixed humid, 4B, which is mixed dry, and 4C, which is mixed marine. Within each of those zones, the building code tells us how much insulation we need to include in different portions of the building envelope. So in this case, we're looking at walls, and we are located in Zone 4. So Zone 4, I would have to have an R13 in my walls. And in my roof or attic, that same Zone 4, I'd have to have a minimum of an R38 in the attics. So walls and attics. So insulation in floors, it's a little bit different. If I have a crawl space situation, and crawl spaces are typically unconditioned spaces, I have to separate the conditioned space, which would be inside, between the unconditioned space, which is the crawl space. So in this example, we're looking at insulation in the floor cavities. So let's take a look at how much insulation we would need to add in that floor cavity if it was a zone 4. So our minimum insulation requirements for floors, come back over here to zone 4, and it looks like we would need in our zone an R19. So if we were in zone 7 or 8, which I believe is Alaska, this is a lot further north, we'd have to have an R38, which is a lot more. It's double the insulation than we would in zone 4. So here's an example. Determine the minimum required R value of insulation in cavities between the studs of wood frame single-family dwelling in Chicago, Illinois. The area of opaque portions of the walls is 1,500 square foot. Total glazed area is 300 square foot. The areas of glazing, an opaque area of the wall is really not considered in this case. So if we're looking for the R value of insulation, we go back to the chart that I showed earlier here, and if you go to a zone 5, which is what Chicago is in, you would notice there that the R value is an R20 for zone 5. So we'd use R20 in the walls. So here's another one. This is minimum insulation requirements for conditioned basements and crawl spaces. So in my case, I live in zone 4 and I have a basement. So my minimum R value for that basement is going to be R10, R13. So I don't have the reference here, but I'm pretty sure that the R10 is for continuous insulation. So that would be your polystyrene board. It would be your extruded board insulation that would be caulked and taped or something like that. That would be continuous. But if we're using a cavity wall, such as fiberglass bat insulation between studs, I would have to have a minimum of R13. And that's what the difference between these two are. So another concept that we need to talk about is thermal bridging. Thermal bridging is an element that's part of the wall assembly that allows energy to transfer through it at a faster rate. So it has less R value. So in this case, where I have a metal stud wall that's insulated, you can see my metal studs here. Metal is a thermal conductor, so that energy is going to transfer through these studs faster than it would out here through the bat insulation. So if I have a bunch of metal studs, which we would in a typical metal framed wall, those studs would represent thermal bridges, and they would be conductors rather than insulators. Same thing with a block wall. So wherever I have solids or solid pieces of that block wall, like the webbing of the block wall, that energy is going to transfer through those webs faster than it would through an insulated core of the block. Even with just air in the block, the energy is going to transfer through the cores at a slower rate than through the solid portions of the webs. So thermal bridging is a term that we would need to remember here. And your next question probably is, well, how would we prevent thermal bridging if I really wanted to build with metal studs? How would I eliminate the thermal bridging? And that's easy. We would just add a continuous exterior insulation to that assembly, just like in this case here. So I have two assemblies here that are equal in terms of R value. Both of them are metal stud, but as you can see here, once we add a continuous layer of rigid insulation on the outside of that assembly, that pretty much eliminates any kind of energy transfer through those studs, or it definitely slows it down. So let's look at this. This would be a 6-inch stud. Is 6 inches of let's see, fiberglass batt insulation. So 6 times 3.5, we would end up with R21. And then it looks like I've got an R3 exterior sheathing on the outside of this, which is insulation. And that's equal to an R11 cavity insulation. That's a 3.5-inch stud wall with an R5 rigid insulation on the outside. So in the end, if we take a look at both these assemblies, it's going to be less expensive for us to build the R11 3.5-inch metal stud wall and the R5 exterior sheathing as opposed to the other side. So the R5 versus the R3, there's not really much of a difference in cost in that. So in terms of cost, we are more efficient to build with 2x4 walls and just a little bit of more continuous insulation on the outside. So the exterior sheathing, insulating sheathing, has a fairly large effect or impact on energy transfer through exterior walls. So we're going to backtrack here just for a minute. If you go back to page 129 in your text, section 5.13, U factor, R or F factor, and C factor. I've already explained U factor, and F factor and C factor are very similar, but they're just for different conditions in a building structure. So my F factor is, yes, my F factor would be in this case where I've got a foundation wall that's that has earth on both sides of it. The C factor relates to a foundation wall where I've got earth on one side and open space on the other side. So you might want to review page 129 again on this. But if we look at heat flow paths, if I have a warm interior, so this is conditioned space up here, here's our insulated wall right here, and if I don't insulate the foundation, if I've got unconditioned outdoor space here, that heat is going to flow through these paths. It's going to transfer through in an arc like this, and it's going to basically move through that foundation wall. So the way to prevent this would be just simply to insulate the foundation. So there are a couple of alternatives for insulating a slab on grade foundation. So if I insulate that continuous insulation on the outside of the wall, which is a good thing, we talked about, that insulation would need to extend down below the finished grade, and then on the inside face of the frost wall, we would use rigid insulation on that face, and that's often used to form up the inside face of that foundation. That's what it would be. So the other alternative would be just to insulate, again, continuous is better on the outside. If this went all the way up and then extended down to the bottom of that frost wall, it would be even better. So this is what it would look like if we were to insulate the foundation of a slab on grade type of structure. So that's going to wrap up Chapter 5, Part 3. And now it's time to take the quiz on this portion of the chapter.